All right, let's get right into it. For the very first time in human history, we have actual photographs of black holes. But these incredible images, they're not just cosmic trophies to hang on the wall. Nope, they're the start of a massive cosmic detective story, one that might just be forcing us to rewrite our entire understanding of gravity.
And this quote, it just says it all, doesn't it? The Event Horizon Telescope, or EHT for short, pulled off something truly mind-bending. They gave us these horizon-scale images of Sagittarius A star, which is the supermassive black hole right at the heart of our own galaxy. I mean, this was a monumental task, but it handed us this incredible, once-in-a-lifetime opportunity to put our most fundamental theories of gravity to the ultimate test.
And here's where the story gets really good. Because buried deep in the details of this groundbreaking picture, there was a puzzle. A subtle but absolutely crucial detail about the black hole it didn't quite line up with what our most trusted, most tested theory of the universe said we should see.
So what exactly was the issue? I mean, what went wrong? To really get that, we have to ask a simple question. What did our reigning champion of physics, Einstein's theory of general relativity, actually predict we would find when we finally got to stare into that abyss?
And this is where things get really interesting. So general relativity predicted that the black hole shadow would have an angular size of about 52 microarcseconds. Now, a microarcsecond is an impossibly tiny angle. To give you some perspective, that's like trying to see a tennis ball on the surface of the moon. But what the EHT actually saw was a central dark area of only 26 microarcseconds. Whoa. That is literally half the size. This wasn't some tiny rounding error. This was a major discrepancy.
Okay, so before we start trying to dethrone the champ, let's give it its due. For over 100 years, general relativity has been the undisputed king of gravity. I mean, it has passed every single test we've ever thrown at it with flying colors.
The core idea is actually beautiful in its simplicity. It says that mass and energy tell space-time how to curve, and in return, that curvature tells matter how to move. You've probably heard the analogy of a bowling ball on a trampoline, right? The heavy ball makes a dip, and if you roll a marble nearby, it just follows that curve. That, in a nutshell, is gravity according to Einstein. So how does that lead to a shadow? Well, the crazy mass of a black hole creates such a deep well in space-time that light itself can get trapped. A really special region forms, called the photon sphere, where photons of light are actually forced to orbit the black hole. It's this sphere of orbiting light that's supposed to cast a dark shadow, and general relativity calculates that shadow to be a very specific size.
And here is the crucial twist in the story. Einstein's theory wasn't totally wrong. That 52 microarcsecond prediction, it turned out to be a perfect match for the size of the bright, glowing ring of plasma around the black hole. But it completely failed to explain the size of the dark patch in the middle. The shadow it predicted was actually the glowing part. So what on earth was the dark part?
This is where a brand new challenger steps into the ring. A theory of quantum gravity called the Nexus paradigm. And let me tell you, it doesn't just tweak Einstein's ideas. Oh no. It proposes a radically different foundation for the entire universe.
So the Nexus paradigm, or NP, says that spacetime isn't some smooth, continuous fabric at all. Instead, it's quantized. You can think of it as being made of a huge but still finite number of tiny, discrete units, almost like a crystal lattice at the most fundamental level of reality you can imagine.
This really frames the difference perfectly. You've got general relativity, which sees spacetime as that smooth, continuous rubber sheet. Then you have the Nexus paradigm, which sees it more like a digital screen, like it's made up of a grid of individual pixels. From far away, it looks smooth, sure, but when you get right up close, it's fundamentally chunky, it's discrete.
And this pixelated view of the universe has a massive consequence. Because of this totally fundamental difference in how space-time is built, the Nexus paradigm predicts that a black hole's actual event horizon, the real point of no return, is exactly half the size that general relativity says it should be.
Okay, so here we are. We have two competing theories with two very different predictions. It is time for the showdown. Let's see how this radical new idea actually holds up when we put it head-to-head against the cold, hard data from the Event Horizon Telescope.
And the result is, well, it's just stunning. I mean, look at this. The Nexus paradigm doesn't just predict the size of the dark spot, it predicts the dark depression, the bright emission ring, and the base diameter of the entire structure. And its predictions for all three of those features land squarely, perfectly,
within the EHT's observational error margins. The match, it's just about perfect.
This chart right here really drives the point home. This is a mismatch score. For general relativity's prediction about that dark center, the score is over 168. For the Nexus paradigm, it's 0.0022. It's not just a little bit better. We are talking about a completely different universe of accuracy.
So, how confident can we really be in this? Well, the combined statistical confidence for the Nexus paradigm's fit is 4.37 sigma. Now, to put that in perspective for you, sigma is how we measure how unlikely a result is due to just random chance. In particle physics, a 5 sigma result is the gold standard for claiming you've discovered a new particle. So, this is getting incredibly close to that discovery level threshold.
And if that wasn't enough to make your jaw drop, look at the Bayes factor. This is a statistical tool that tells you how much more strongly the evidence supports one theory over another. In this case, the data favors the Nexus paradigm over general relativity by a factor of 10 to the power of 36. That is a 1 followed by 36 zeros. The evidence is, to put it mildly, statistically overwhelming.
So, wow, what does this all mean? If this new theory continues to hold up under more scrutiny, this isn't just about understanding black holes better. This could be the very first crack we're seeing in the foundation of 20th century physics, pointing us toward a completely new understanding of our universe.
You see, the Nexus paradigm doesn't just stop with black holes. Its proponents claim it offers potential answers to some of the absolute biggest unsolved mysteries in all of science. It suggests a path to finally uniting gravity and quantum mechanics, the holy grail of modern physics. It even proposes brand new explanations from the ground up for those mysterious things we call dark energy and dark matter, which, remember, make up 95% of the known universe. This isn't just a new theory of black holes, this is a serious candidate for a new theory of everything.
Now look, this is just one set of observations, and science, rightly so, demands extraordinary evidence for extraordinary claims. But the data from that very first fuzzy picture of a black hole is forcing us to ask a really profound question. Are we just tweaking our old picture of gravity, or are we right now witnessing the dawn of a whole new era of physics?